All right. So this is Exam1, and so it says that a dam um, with vertical height, capital H. This dam's height is capital H, can be approximated as a trapezoid with bottom and top width of capital B and T. So this width over here is capital B, and this width is capital T, respectively. Now, and it's asking if the water level is lowercase h. So we have the water in here with the water level being at h. Okay, and so we're asked to write an expression for the horizontal force exerted by the water on the dam. So first thing we know is that force is equal to pressure times area, and now we have two components in our force equation that we have to find expressions for. Okay, so first thing, let's start with pressure. All right, and let's just go ahead and say that at the top of the water level, let's call that our height is 0. Okay, and then at the bottom here, we'll call that some height Z. And so we know that pressure is equal to the atmospheric pressure plus density times the gravity of water times whatever depth you're at underwater. And because we're not working with ideal gas law, we don't have to worry about this atmospheric pressure. And so we can just cancel it and use the gauge pressure. And also knowing that, we can say that since the top of the water is out in the atmosphere, that pressure here at h equals 0 can be is equal to 0 as well. Okay, and so what this leaves us with is pressure equals rho times gravity times height. Okay, so now that we have an expression for pressure, all right, let's find one for area. All right, so for area, let's redraw this. So we have our trapezoidal dam. It's got some water level here, and so to calculate area, we can split our dam into very thin slices, with each slice having a height of dh. Okay, so with each height having a height of dh and some width r. Okay, let's call this bottom here r. So we can say that the area is equal to width times height, all r times dh. But the one thing we have to keep in mind is, since this is a trapezoid, as you go up the dam, the width of our slices is actually increasing. Okay, so we need to express our r in terms of height. Okay, and now we need to find this expression RH to account for the changing width. Okay, and to do that, we can start by so we're gonna say that at h equals 0. Okay, so our r of 0, and we made our h equals 0 up here at the water level, but in this case, when we're trying to find the expression for our h, we're gonna say that h equals 0 at the bottom. And the reason we do that is if you have a water level of 0 at the bottom, your water level is gonna be all the way at the bottom, and as your water goes, like grows, it goes up, you're gonna need to, account for smaller and smaller pieces as you go up. Okay, so at h equals 0 at the bottom, when we look at our trapezoid, we're given that that is the width is capital B. Okay, and then the other width we know would be at the top of the dam. So our H, okay, big H. All right, so at our capital H, we know that our dam is with capital T. Okay, all right, and so since the width changes linearly, we have to use the slope, and the slope is rise over run. Okay, so what ends up happening is since the slope is rise over run, so we got t minus b all over run h minus o. Okay, which is simply t minus b all over big H. Okay, so now we found our RIH, which is equal to capital B plus T minus B all over capital H. Okay, and now, okay, so we have got our expression for RIH, the rate that the width is changing according to time to height. All right, and so we can come and replace that, put that into our area equation. Okay, and so our area equation becomes this. Replace that our area becomes capital B plus T minus capital B over capital H. So this times dH. Okay, so we got area, we got pressure. Now we can just plug it into the force equation and work out an integral. Okay, so force is we're gonna say that dF, okay, it's an integral, dF is equal to pressure. Okay, so rho gh is calculated here, okay, times the area, so this whole thing, so B plus T minus B all over H times H. Okay, and then with this slope, I don't know if I talked about it. It's now you start at the bottom at B plus the rate as you're going up times whatever depth you're at, whatever depth of water. Okay, and times dH. Okay, and now we're gonna integrate this thing, and first thing we're gonna do is we're gonna integrate this side, and the way we're gonna do that is start from 0 to f of x, which is the total horizontal force pushing on the dam wall as a result of the water and that's what we're looking for. That's the expression we're working to find. Okay, and then this side over here is gonna get integrated from height 0 to height z. So 0 from the top all the way down here, which is h, which basically equals z. Okay, and then now that we have our integral, we just solve it. And once you solve this integral, you're gonna find out that it's gonna equal to, that's the biggest question that we're looking for. And then once we solve this, we find out that f of x, the total horizontal force exerted by the water on the dam, is equal to rho g z cube times 2t minus 2b times z plus 3h b, and this whole thing all over 6h. Okay. So when we look at this, well, it's telling us that if you have a trapezoid, a water dam with a trapezoid, and you were given the bottom width, you're given top width, and you're also given the big H, you can find out the horizontal force exerted by water on the dam at any given depth, z. Okay, thank you.